Good afternoon, morning, evening, whatever time you've decided to watch these videos. Welcome back from spring break. I hope you had a wonderful break. You were hopefully at least able to do something good for your mental health and take a few days to rest and for yourself. But now we're back in it, right? We're back into the groove. So hopefully you were able to get rested so that we can finish strong. So we're about halfway through the semester. And the nice thing, or kind of a nice thing, is that in a couple of weeks, we also have a flex day. So on Thursday, April 20th, we have a flex day, meaning no classes. So almost like a little mini break right after the big break. So that'll be kind of nice. But we will still have our early in the week videos. So just kind of FYI with that. So if you recall, back to things that we had finished talking about when we saw each other last, we started finally talking about the ocean. I know, super wild that we don't even talk about the ocean until about halfway through the semester, but hey, it's just how the cookie crumbles, if you will. So if you recall back to, what drives circulation, we had like the surface circulation stuff, and we have the thermohaline circulation, which is temperature and salt, and recalling like where that starts and why that's important. And what I want to finish up talking about today in terms of circulation is kind of like these smaller scale circulations that we see at the surface and how we measure currents. And then from here, we'll jump right on into chapter 8, talking about waves. It's a pretty quick chapter, and then we'll get into talking about tides. So we'll probably get to tides when we return together on Thursday, but just to kind of give a brief rundown. So with all of that said, let's knock her on through. One more thing. Just some reminders for some of our assignments. I know that some of us are still a little bit behind on getting some things in. So if you're still working on your personal letter, please get that in as soon as possible. And I will be chipping away at grading your second exams, the short answer questions. I'll be working my way through those this week. I did not really get around to doing any grading. Mother Nature went buck wild on Friday in the Midwest, so I was kind of monitoring that whole situation for a majority of that day. And just a lot of other life things have come up. So I apologize that things are, as usual, a little bit delayed, but thanks for your patience, and hopefully we'll get through that soon. Okay, any whoosies. Returning back to surface circulations. So if we return back to this idea of convergence and divergence, we talked about these two terms before, and more so when we talked about plate tectonics, right? Convergence means coming together, divergence means going away. Excuse me. And these little things here in the schematic are called Langmuir cells, which are helixes or near surface wind-driven water motion. So it's kind of like this sort of like within the little surface area here. Remember that this can kind of penetrate down further depending on how strong the winds are. If the wind's not very strong, then you're not going to have that much circulation going on. And these cells can extend downwind to form these windrows of surface debris along the convergence regions. That's not a typo. Windrow is an actual word. So they're kind of like these little circulation things that, in like foam almost, that you can literally see in the water. It's actually kind of cool. And the sinking material is then swept into zones of upwelling water. So there's basically just a lot of like these little miniature circulations of upwelling and downwelling occurring here. And so this is what they look like. This is a really neat picture, I think, kind of showing, if you've ever seen this in the water before, now you know what they are. So they can be spaced anywhere from 5 to 50 meters. And the closer together they are is if the thermohaline depth is shallow. So remember thermohaline, that was that term of like a sharp change in, or excuse me, not thermohaline, thermocline, where there's that sharp change in water temperature in a certain level of depth. So if you have a really, really shallow thermocline, then you're going to see these windrows to be much closer together. But if you have a really deep thermocline, then they're going to be spaced further apart. And the vertical extent of these is about 4 to 10 meters, again, depending on how windy it is and how shallow the thermocline is. This really also helps mix surface waters around and distribute nutrients. Even in relatively nutrient-poor places, there is still this circulation that exists. What's also really fascinating, and I know we talked about, things like upwelling and downwelling in terms of gyres and western intensification and, Ekman transport and things like that. But there are other areas of permanent convergent and divergent zones around the world's oceans. There's generally convergent zones near around 30 degrees north or south, and these can generally mark the center of large ocean gyres. There's also convergent zones. There's also more convergent zones near 50 degrees north and south, which are regions of downwelling and low productivity. And when I say that word productivity, it basically means life, like biological life. So is there plankton around, or is there not? Is the plankton helping drive in smaller fish, which brings in bigger fish, etc. So if there's low productivity, that just means that there's not a whole lot of life happening in that zone. And then we can also see here that upwelling is associated with 3 major divergences and helps deliver nutrients and supplies massive food chains. So for the most part, we actually will observe that the open ocean areas are actually pretty well big old deserts. It's really quite fascinating, but there are little areas where there can be some areas of productivity, which is really quite nice. And here's just another reminder of what upwelling and downwelling can visually kind of look like. So on the left, starting with upwelling, we're looking in the northern hemisphere, by the way. We have cyclonic wind, so this counterclockwise motion for basically a low pressure system. But the overall Ekman transport is, remember, 90 degrees to the right of the wind motion. So you're pushing water away from the center of a cyclonic wind. So then you would cause upwelling to occur. You're bringing up water from the deeper oceans, whereas the opposite would occur in terms of downwelling. So you have anticyclonic wind, in this case, a high pressure system, so clockwise motion. And again, 90 degrees to the right of wind motion is the net transport of water. That's good old Ekman around here. So that would cause overall surface convergence, which would then give us downwelling. So it's not like when we have these water systems coming together, or convergence and divergence, it's not like we have like a crazy tower of water like shooting up from the surface of the ocean. That's not the case at all, because of surface tension and gravity and things like that. So just a little visual of what this can look like. And then this is looking at the equatorial upwelling, is most developed in the Pacific. So the positive values here indicate upwelling and negative indicate downwelling. And this is wind-induced upwelling, by the way. So this is in centimeters per day. And what's actually kind of cool is you can really nicely see this huge couplet almost of like these upwelling zones and downwelling zones on either side. It's almost like a big old belt around the planet, which is really quite fascinating, I think. And you can also see it really nicely off the coast of South America. You can also even see it here off the coast of California. And if you recall, upwelling is a huge piece of our puzzle here. It helps make our kelp forests thrive and survive like they have been able to. And a lot of creatures around here really depend on that process. So to finish up the video for today, I want to talk about measuring currents. So how in Tarnation do we measure these? Well, there's basically 2 ways of direct measurements. One, you can literally follow a parcel of moving water, There's a way to do that with drift bottles, basically, but also measuring the speed and direction of water as it passes a fixed point. So you can basically have an instrument on something and it can measure how fast the water is moving, which is kind of a cool thing. So on the picture here on the left is looking at surface buoys, which are in the red here, which are being deployed from a vessel. So buoys tend to be connected to the bottom of the ocean in some way, shape, form, or another. Your book has a pretty decent picture of what these things can look like, and they can be completely submerged underwater, or they can be above water, much like this. One second. And it can be a whole thing, which is kind of fun. Then we also use satellite altimeter data, which can help give us a global picture. And this helps determine the roles of gravity and periodic tidal motion, air pressure, and geostrophic flow of producing sea surface topography. So satellites are great, but they are far away and they are making estimations. And, that can be kind of a thing. But they are very, helpful in seeing the overall big picture, which is nice, as opposed to just one particular location. And then drift bottles. So these are thousands of sealed bottles, each containing a postcard released at a known location. When they are found, the finders are asked to record the time and location of said postcard, and the actual path of motion is then assumed. So it's, unless there's like a certain tracker in there, but kind of an interesting way. If you refer back to the video, the TED Talk that we watched in class, where there was that basically release of the, or I can't think of words now, but it was, there we go. It wasn't intentional. But the ship that capsized and then released a bunch of those rubber duckies, and then been able to see them as they have gone around the world, which is really quite fascinating. So overall, here's a recap from chapter 7. So we talked about the ocean structure and circulation. So we observed how salinity and density vary with depth, as well as along the ocean, so at the surface as well as going below. The thermohaline circulation, upwelling and downwelling, surface currents, meaning Ekman transport, and western and eastern boundary currents, and measuring currents. I do want to note that one thing that your book does go through that because for time restrictions, we don't really have a chance to do this, is talk about the changing of the sea surface circulations. So there's a couple of oscillations out there that you can look into further if you want for your own knowledge, but we will not be covering it in terms of official material. So, of course, if you have any questions, comments, or concerns on anything, please holler at me and let me know. But hang tight for the next video. Thanks for watching.